Building a personalized AI chatbot from scratch is an incredibly rewarding project because it allows you to create powerful interactive tools tailored exactly to your specific needs. Let's walk through how we construct this using three primary building blocks. First, we use Streamlit, which acts as our web interface. It's brilliant because it transforms simple Python scripts into interactive websites without needing to know HTML or CSS. Second, we use Google's generative AI. This is the brain of our operation, connecting us directly to the Gemini models to handle the actual reasoning. Finally, we bring in the OS module for our file system operations, which will be crucial later for tasks like creating folders to store our chat logs. Let's look at the first step, UI setup and configuration. Before we put anything on the screen, we need to define the global attributes of our web page. We do this by calling setPageConfig. This defines the page title on the browser tab, the icon, and importantly, sets the layout to wide, ensuring our chatbot uses the full width of the screen. Next, we build out the visual structure using title and caption elements. If we need bolder text or headers, we use the markdown function. Streamlit also makes it easy to add interactive elements. For example, adding a button that triggers a fun balloon animation takes just a couple of lines of code. And to actually see all of this running during development, you simply execute the Streamlit run command in your terminal. Moving on to step 2, our chatbot needs a secure API connection to communicate with Google's servers. To keep your API key hidden from anyone looking over your shoulder, we place a text input in the sidebar. By setting the type to password, the characters are securely masked. Once the user enters their key, the application attempts to authenticate the session by configuring the generative AI. We have logic here to handle the outcome. If it's successful, we show a connection message, but if the key is missing or invalid, we prompt the user with a warning. This safely prevents the app from contacting the AI without proper authorization. Now, a good chatbot needs a memory to keep track of the back and forth conversation. In Streamlit, this is handled in step 3 using the session state. If a list of messages doesn't exist yet, we initialize it right here with a default greeting from the assistant, like hello. To make this feel like a real chat app, we use a loop to iterate through every message in that session state, displaying the history on the screen. For new interactions, we provide an input box at the bottom. When a user types a prompt, it is immediately appended to the session state, so it becomes a part of the visible history. Finally, in step 4, we actually connect to the Gemini model. We initialize our AI by selecting the Gemini Pro model, which is a fantastic general-purpose large language model. When the user submits their prompt, we call the generate content function. The AI's response is captured and then appended to our session state, so it shows up on screen as the assistant's reply. While we are using Gemini here, the architecture is flexible. You could easily swap this out for other models like OpenAI's GPT-4 for conversational tasks or Anthropic's Claude 2 if you need strict instruction following. The ultimate takeaway here is that Streamlit handles the interactive interface and state memory, while the generative AI handles the complex reasoning, seamlessly working together to build a functional app. Now, keeping this conversation active in the current tab is great, but what happens if the user accidentally refreshes the page? We'll need a way to save this data permanently using local storage. To prevent your chat history from disappearing every time the page refreshes, we need to implement a local storage system. Let's look at how this is done in the first section. First, we need a way to identify each conversation. We do this by generating a unique chat ID using the current timestamp. As you can see, this integer is formatted into a string, which gives us a completely unique name for every session. Next, we need a place to store these sessions. Using the OS module, we create a folder named Database. We then proceed to save the chat logs as text files right inside this directory. To make this user-friendly and allow people to revisit old conversations, we use another command for reading the contents of the database folder. We take these file names and populate a select box in the sidebar. This seamlessly lets users flip between starting a new chat or picking up an old one. Now, let's move down to the second section to talk about robustness. Technical issues happen. Maybe the internet drops or an API key is invalid. If we don't handle these, the app will crash. To prevent this, we are wrapping our API call in a standard try except block. If the call succeeds, great. But if there's an error, instead of a crash, we show a clear, friendly error message to the user using Streamlit's error function. We also want to make sure the user knows the app is actually working while waiting for the AI. So we use a spinner to show the system is thinking. And if they forgot their key altogether, we provide a gentle reminder to fill in the API key before they start typing. Finally, over in the third section, let's look at how we handle advanced history management. As conversations grow, we need to efficiently manage the context. We use a lambda function to cleanly append the new chat to the past chat, resulting in a completely merged chat history. When we are dealing with complex Python objects like these, lists of dictionaries, simple text files can be problematic due to formatting errors. Instead, we use joblib.dump to serialize and save them. This preserves the exact structural integrity of the data. Then, when the app restarts, we simply call joblib.load to efficiently reconstruct that exact original object. This is how we build a truly robust and user-friendly interaction loop. With our application infrastructure solid, we can now pivot to understand how AI models measure similarities, starting with algorithms like KNNS. We just talked about how an application might store chat data locally. Now let's look at how an AI might actually search through and classify stored data. Starting with the fundamental concept, K-nearest neighbors, or KNN. This algorithm is what we call a lazy supervised learning. Why lazy? Well, if you look at this brain icon here, notice that it essentially has no actual training phase where it learns complex rules upfront. Instead, it literally just stores the entire dataset in memory and sits there doing nothing. It only performs calculations exactly when a query is made. But when a query does happen, how does it know which data points are relevant? It relies on distance formulas to figure out how mathematically close points are to each other. The most common one is the Euclidean distance. Without getting bogged down in the complex symbols, this formula simply calculates the direct straight line distance between 2 points, exactly like measuring with a physical ruler on a piece of paper. Alternatively, we have the Manhattan distance. Instead of a straight line, it sums up the absolute differences across each axis. This looks exactly like navigating through city blocks. You can't just walk diagonally through buildings. You have to go over, then up, then over again. Finally, there is the Minkowski distance, which is basically a master formula. See this p exponent. It lets you toggle between the other two. If we slide this p value to 1, the math turns into the Manhattan distance. If we slide it to 2, it becomes Euclidean. Let's see this in action with a concrete example, where k equals 3. Imagine a new piece of data comes in, represented by this green star query. The algorithm measures distances and draws a boundary to find its 3 closest neighboring points. Look closely inside this circle. We have 2 blue circles and 1 red triangle. We simply let them take a vote. Since the blue circles hold the majority, our system outputs a predicted label of class A. Now let's contrast that simple lookup method with the broader generative AI landscape. Modern generative AI models don't just store data. They absorb patterns from massive datasets in the cloud and process them through deep transformer architectures. These complex neural networks act like powerful reasoning engines that can actually create entirely new content, whether that's text, beautiful images, audio, video, or even writing code. To steer this massive creative power, developers use control knobs. You can turn up the temperature dial to make the model's output more creative and random. And you adjust the max tokens dial to tightly control the maximum length of its response. If you are choosing an AI model today, let's compare 2 major families. On the left, we have Google Gemini, particularly their Flash and Pro models. They are highly favored for having strong multilingual support across the globe and offering a very generous free tier to get started. On the right, there is the OpenAI GPT family, like GPT-4. These models are famous for their very large context windows, which acts like a massive short-term memory, allowing them to analyze huge documents all at once,
alongside their incredibly robust coding assistants. The core takeaway here is that while traditional ML algorithms like KNN simply look up existing patterns from stored data, modern generative models synthesize entirely new outputs based on complex learned representations. Your ultimate selection between these models depends on your strict project budget and how much speed or latency your users demand. As we start building these intelligent systems, we'll quickly see why simple local files are enough, requiring us to explore robust storage strategies for production apps.
For production-level applications, storing chat history requires robust strategies. Local file systems are fine when you are just prototyping, but as you scale, you might shift to shared network drives to centralize your logs across a team. For true scalability, cloud object storage like AWS S3 or Azure Blob keeps data in accessible buckets. And for advanced AI features, vector databases like ChromaDB store data mathematically, allowing you to perform semantic similarity searches rather than just matching exact keywords. Testing these systems involves setting up a retention policy, perhaps keeping logs for 15 to 30 days. This creates an audit trail, enabling quality assurance teams to do a review of the text logs directly through the Streamlit sidebar to ensure answers remain safe and accurate. Moving over to how the AI actually communicates, let's look at LLM chat interaction design. We manage context using distinct roles. The system prompt defines the core persona. For example, explicitly instructing the AI that you are a professional banker anchors its behavior and prevents it from hallucinating or answering out of scope questions. Then we have the user, who is the person typing the prompt, and the assistant, which represents the AI's response. When making an API request to a chosen model, you must pass this full, ordered list of messages so the model understands the entire conversational context. Of course, when building this, you will encounter errors, which brings us to debugging strategies. If your stack trace highlights an error at line 32, you need to carefully inspect that exact line for simple typos or missing parentheses. A common error like module not found usually just means you need to run pip install for a missing library. Meanwhile, a type error often indicates you are passing data in the wrong format. To accelerate this development process, you can leverage low-code AI assistants. Windsurf is incredibly powerful for project scaffolding. It can generate your entire folder structure, requirement files, and UI from a single natural language prompt, making it perfect for end-to-end prototypes. GitHub Copilot, conversely, is fantastic for auto-completing smaller code snippets as you type. Setting up your workspace correctly is vital. For environment setup, you'll first run pip install Streamlit. It is heavily recommended to use a virtual environment to keep your project packages neatly separated from your system-wide packages. If your IDE throws a warning that an import could not be resolved, you should check your Python interpreter settings. Once everything is set, running Streamlit run app.py will successfully launch your interface in the browser. Finally, a crucial architectural concept is Retrieval Augmented Generation, or RAG. This framework grounds the AI in reality. When a user asks a question, a retriever searches an external database for relevant documents. These documents are then fed into the generator, which formulates a grounded, factual answer based only on that retrieved context. Understanding RAG is a vital component of career prep for AI roles. As you use these tools to learn data structures, always ask your AI assistant to explain the code rather than just writing it for you, ensuring you truly internalize